So, good morning. We are discussing about the microcontroller board Arduino Uno, right. We are discussing about that, and we have seen several features of this board Arduino Uno, where we have got the analog pins and digital I/O pins, and we have got analog commands for analog write and analog read. And most importantly, what we saw in the last class is that it has also got some built-in PWM circuits, which can generate pulse width modulated signals. And by that, as we modulate the width of the pulse of say this pattern versus if I have this pattern, obviously the average voltage is more in this case, right. So, accordingly at any output I can change the average voltage by changing the duty cycle of the pulse width modulated system. Okay. And that is a very nice feature that we have got in Arduino. Now, besides that, we will today start discussing about how this Arduino board will communicate with a PC. For example, let us look at this scenario. We have got a laptop where even say we said that you will program this Arduino board, and for that you will be writing some programs here, and that program will be downloaded into this Arduino board. And this mode of communication in this case is serial communication. We will see in detail other modes of communication. Now, in serial communication, as we can see, information passes between the computer and the other host through the USB cable. It can be an USB, here it is being shown in a USB, but it can also be in a serial mode. Now, USB protocol is a little more complex, and for that, whenever we are having something serial, that serial to USB conversion is required. For that, there are separate chips available. Now, here for example, this serial pattern is 1 0 0 1 0 1 0 1 0 etc. So, this is very familiar to you, and usually in the normal scenario, we assume 0.5 volt to be 5 volt to be a 1, and sometimes say 0.5 volt less than this thing to be a 0, or just the other way around if it be negative logic, that is known, right. Now, if we look at the say a single character, a single ASCII code of say B, and I am sending that as 0 1 0 0 0 3 zeros 4 zeros 1 0. So, that will translate to low high low 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 high low like that. Now, therefore, that will be coming through some, I will have to send some 0 here, then some 1 here, and then 4 pieces of 0 here, then 1 high here, and then 1 low here. Now, when I do this, besides, so I am actually toggling a pin to be 1 and 0, 1 and 0 like that. But I can do that in this way, that I have got one pin and I am just toggling it 1 and 0, or we have got this digital write and where. So, how do I toggle it? Digital write 1, say 1, and then delay. and again I can do digital write. In that way I can do it. Okay. Now, I need one single wire to send the data from this system to this system. Now, this receiver, if I call this to be the receiver and this to be the transmitter, the receiver must know when the data has started flowing, because this data, say this line is a TTL line. Okay. This is a transistor logic being used here. Now, this is a line, when this nothing is floating, it is actually in 1, say it is in the high level. Therefore, whenever I want to start transmitting data, I will have to send a start bit first. Which brings this TTL level to low, and after that it be 1, 1, 0, 1, whatever I go on sending. So, that is being sampled at the middle of each of these clocks. All right. So, we need a start bit. Similarly, since I am sending the serial data, I must also tell the receiver where is the stop bit. So, for that the stop bit is again 2 bits of zeros. All right. Usually, we know that it is an 8 bit data, or so I will wait for the start bit, and after start bit I will sample it 8 times, and after that I am expecting 2 stop bits, and with those 2 stop bits I can say that that particular packet is over. Now, a very interesting and very simple task that you can do is that a transmitter is sending data in a serial form, and in the receiver where there is a system and there are some buffers, etc., you convert it into a parallel, you are loading it in a register, and that is very simple, that you can do using a shift register, or even in a memory location you can do that easily, right. So, then it becomes a parallel data, and then if you have some parallel out ports, say 8 bits, 8 lines coming out of this, then this entire data can be transferred in a parallel form. Okay. Now, the serial commands, you need not memorize it. So, for Arduino there are some commands like serial begin. For example, we can say serial dot now, what does this mean? This means I am going to send at 9600 bauds, right. This is the baud rate, that is the bits per second. So, 9600 bits. So, as soon as I start with this information, then this sampling periods are fixed. I will have so many bits coming per second. So, I can very well sense them. Similarly, there are other commands like serial print, or sometimes serial print ln. You can say some value, you can put some value here and you can print it. Similarly, you have got serial read. We will use some of these. Serial available tells us whether a particular serial port is available, whether it is not being involved in, whether it is being involved in some communication or not. Similarly, with serial read we will have serial write, and one a little uncommon is serial parts int. This is if there is some event coming from, say for example, a keyboard, a particular key, there are several keys and each of these keys are encoded. If any of these keys are pressed, then the value of this, the value corresponding to this key, whether it is key number 1 or key number 2 or key number 3, that will be parsed and will be received by the serial port. We will be using it as an exercise a little later. Okay. Now, we can have two different communication protocols. One is of course serial, and we said if the baud rate is 9600 bps bits per second, then we know that time per bit is 1 by 9600 second. So, whenever I am having a signal pattern like this, whatever, and I am actually sampling at these points at 1 by 9600 seconds. So, this time is right. So, that is how we know whether it is a 0 or a 1. Okay. Now, the USB protocol, one is this is the serial protocol, and on the other hand we have got the USB protocol, which is rather complicated. I am not going into the details of that here, but one thing that must be mentioned here is the voltage signal in an USB transmission is sent through in a differential pair, like that. Here is sometimes we use twisted wires also, that say I am sending some signal here, some data in a particular phase, and here I send the data in the other phase. Why? What is the reason for doing that? The reason for doing that is, suppose I have got some data. Let me try to draw some data, and that is a D plus, say, analog data I am showing. And if there be another data, I am just sending it in the other phase. Now, while transmission, I am transmitting them through some channels, and the channels are always having some noise. So, the noise will affect both of them, right. Now, if I take the differential of these, I will get the actual data, because the noise will be cancelled out, because it is being sent in a differential mode. So, if I just draw say some data like this, another data is like this is the D plus, another data is coming and is just the opposite of this. Now, then from these values we can say for example, this one is say some k, and this one which is you can see the amplitude is more, right. We will send them to as A to D. This is might be j, some other data, all right. This one is again at the same level, this will become k, like that it will go on. So, we are doing differential decoding. Another point is the signals are sent in a non-return to 0. Non-return to 0 means here say I have got some signal and here is my 0 level, this is my 0 level and this is suppose 5 volt. In normal case I had 5 volt and 0 volt or 5 volt or 0.5 volt, and here it is minus 5 volt. I am not sending it to 0, all right. That has got some extra advantages for error corrections, which we will see later. And might be this you already know when you have learnt about Manchester decoding and all those things. Now, USB, say for example, between each of these data there is depending on the frequency, say I have got 12 megahertz in our case, say will be that means around 83 nanosecond is the difference between these 2 points, these things. Now, after this entire data that is coming up is put up in a packet format. Now, the packet format is rather complicated. I will just say that there is a start of packet, the start of packet is required for synchronization of the clock, then the packet ID, so there we send the LSB first, the packet ID will go, then the LSB first, and then there will be an end bit, and at the end there will be an end of packet. So, if I have got something coming out from the serial port and I want to communicate through USB, then I need a serial to USB converter. Most of you have seen such connectors, right. And what it does is, it takes this protocol or the USB protocol and or say for example, I have got the serial bit shown here, I do not know why I gave the gap here. So, you have got the serial bit here, and that serial bit will have to be encoded with the start packet and end packet, and also we have to transmit it using this non-return to 0 protocol, non-return to 0 and through differential pair and vice versa. So, but the thing is much more complicated. So, we are not going into details, but you have got converters available for that, right. Now, we had shown I think in the earlier class, correct me if I am wrong, that how using the Arduino board we can blink an LED, right. We have seen that. Now, suppose you want to, I am just giving you an exercise to do. Now, suppose you have got the LED here and I have got a keyboard here, and the keyboard has got whatever say 6 keys. So, 1 to 6 values are there. So, depending on the key that is pressed, you will have the Arduino here depending on the key that is pressed, you will glow the LED with different intensities, and this thing you can read using the serial dot %% method. And so, it comes over here and this LED will glow with different I mean when I put 6 means full glow and 0 is not there. So, let us put a 0 here. 0 is off and 1 is minimum intensity. Okay. So, you try to do that if you get access to an Arduino board, or you can try to do that in any microcontroller that you get, okay? Not necessarily Arduino. Is the assignment clear? So, okay. So, you can try that. Now, whenever we talk of a microcontroller, we need to talk about all the microcontrollers communicate. One is the serial. One is serial communication that we know through USB, but there are asynchronous communications also. What is the difference between synchronous and asynchronous communication? Yes, synchronous communication means all the communications are with respect to a clock tick. So, it may be at every tick, it may be after 5 ticks, every 5 ticks, like that. Asynchronous means it can happen anytime, right. Not synced with the clock. All right. That is asynchronous. Now, the best way of one of the very popular ways of dealing with asynchronous communication is interrupt, and I think I do not need to repeat interrupts in any way, because all of you know what interrupts are, right. Can I assume that? Right. So, an interrupt is asynchronous. Now, although all of you know what an interrupt is, often I find when I ask the students what is an interrupt, they mess up. Okay. They say interrupt is a pin, interrupt is a signal, whatever it is interrupt is an asynchronous event that causes the execution of the process to temporarily stop, interrupts the flow of the process. Now, this can come from a hardware source, it can come from a software source. Accordingly, we can have a software can generate also an interrupt in the process, or from hardware devices. Whatever in the case of hardware devices, we have got the processor, and the processor is actually executing the process that is executing here. Usually, there are pins through which the external device, some external device sends the interrupt, some signal, and that signal is received by this. If the interrupt is not masked deliberately, not disabled deliberately, then that will be acknowledged and this program will be interrupted somewhere. And you know that whenever an interrupt occurs, then we will remember the status at this point and then go to some interrupt service routine, and again after servicing we will come back. So, what we need, sometimes there is again, just since I am talking about interrupts, let me complete it. Hardware interrupts can be just like this, or they can be vectored. If it be just like it comes to a pin, and there could be number of devices which could be connected to the pin, I do not know which device has interrupted, either this has interrupted or this has interrupted or this has interrupted. I will have to, I means the processor will have to check the flags of each of these who has interrupted. The other option is to go for a vectored interrupt. That means, whenever the interrupt comes, here is the processor and the devices are there, and I have got a pin, and an interrupt has arrived at this pin, and along with that some more information is sent to me that tells me which device has sent the interrupt. So, these devices can send the interrupt here, and this device, this interrupt controller, can connect to the interrupt pin of the processor and feed in this extra information of which device has interrupted. This is known as vectored interrupt. In between, we had the solution. If we had individual pins for each of the devices, then the thing would be simplified, because from the pin itself, there are different interrupts, and by the interrupting pin I could have identified which one is interrupting, right. So, interrupt plays a big role in Arduino board. In our Arduino environment, pins 2 and 3 can be used as an interrupt pin. We have got special pins like here 2 and 3 can be used as interrupt pins. Okay. And for that, we have got also Arduino commands, attach interrupt, function, mode. What does it mean? For example, if I write zero, say encode falling. That means, I am attaching a particular interrupt to the interrupt pin 0, 0 and 1, pin 2 and pin 3, and the interrupt is activated at the falling edge. That means, it is an edge triggered interrupt. Whenever this becomes like this, then it is an interrupt. Okay. And this is the function that I have to execute. This is the interrupt service routine, that I will, as some interrupt falling edge occurs at this pin, this interrupt, 0th interrupt, will be activating the interrupt service routine do encode. No. There are two interrupts. So, 0 and 1. So, pin is this. Yeah. So, here I am just writing a small piece of code for interrupt. I think it will make it clear. State is a variable whom I have just set to 0, then set up. You remember that we have got the pin mode. To set the pins, we say LED with the output. So, whenever there is a change, I will invoke this interrupt service routine blink at this interrupt point. So, this is over. LED gets state, and what was state here? State was low, right? State was low. So, and I think I am visible, void blink, it will be state will be the not state. Now, let us see what will happen. This blink, right. So, whenever there is any change at this pin, I will go to this function, all right. And so, what and there is an infinite loop that is going on. So, and I will just toggle the state, and then I will come here and digital write that state. So, 1 0 1 0 that will happen at every interrupt. Otherwise, if there is no interrupt, this blink will not be activated. Therefore, the state, the LED will be in the same level. So, this is how we can, this is a very simple interrupt. Here we have not done any inside this interrupt service routine, we have not done any complicated things, but whenever the interrupt comes, obviously all the page fault interrupt handling tasks are taken care of. Okay. So, this is a very simple way in which we can write interrupts. Another important component is the timer. So, we have got a number of, now this is something that will come back to our embedded system discussions time and again. Time is a very important parameter, and we will have to deal with different versions of time. So, the timer here, there are some very simple commands like timer functions. There is a library, just like we include libraries, there is a timer .h library, and we have got commands like int, say function every, it is called long period callback. That means, say callback is a function, that means the callback is some function that will be carried out every long period is just like long int, all right, if after every period. So, this function suppose works. So, that is a regular, this means what? This callback is a periodic function. It takes place here. So, here the callback has started here, and then after a fixed period, whatever that period is, I specify that here, again callback, and then there is a this thing same period. So, this is the period. So, this is a periodic systems are very important in real time systems and embedded systems. So, I can define a periodic system using this, all right. The next important declaration is int every long period callback repeat count. What does it do? It will carry out same thing. Here it was a periodic thing, it will go on and on and on. Here I give a count, say n number of times, he will call this callback. So, this will be callback function, this periodic function will be instantiated n number of times. All right. The other thing is, this was period, but suppose I write after. So, in this case, what will be the scenario? Suppose a value of n is 2. Suppose in that case, this will take run once, run twice, and then stop. All right. Now, if I say int after, long duration callback, what happens is this callback is activated once after so much duration, all right, so many period milliseconds, and returns the ID of the timer event. The other important function is after a particular duration, the callback function will start. No, if you want to make it periodic, in that case you will have to define it as periodic. So, whatever is the duration, after that it will be activated. The other important function is int is oscillate int pin long period something. That means, pin is a particular pin, and what I am saying is after every period I will toggle the state of the pin. So, suppose this pin was 1 and after this period p I will toggle it, all right. And so, this p is say in my 1, 2, 3, 4. So, 1, 2, 3, 4, a little bit more, and then it will be again toggled up, all right. So, it is oscillating, and the starting value, whether it will start from 1 or it will start from 0, is decided by the starting value, which can be, this can be high or it can be low, all right. Now, this also, all right, this is used for oscillation. Now, I can also add this just like this, the same thing, int. Now, this means what? It will go on forever. So, I can check that also by just saying int oscillate all the other parameters like int starting value followed by another integer, that is the repeat count. All right, that is a repeat count. That means, it tells us that it will go on for so many times. It will be so many number of say repeat count is 5. So, 5 such oscillations. This is one oscillation, 1, 2, 3 like that. So, using this timer function, we can generate different timing events, which will come in very handy when we will be handling real time events and real time operating systems, scheduling and all those things. We will see that this will come in very handy. There are a couple of timing functions still left, which we will do tomorrow, and after that I will complete the controller.